washer's method. Then the idea here, you need to take that as as closely as possible to the idea of using this method. So now let's say we have a region, right? Starting out with a region here. So just a little bit unlike with the earlier kind of problem. Now the rotation axis, either the x-axis or the y-axis, now the rotation axis itself is no longer aligned with one of the boundaries. Okay? So in the earlier case, when it was a disk, and think about it, I mentioned clearly that once one boundary side right here got to be a straight edge, right? And then we put the rotation axis right there. And so that's why when we were rotating it, we got the nice solid stuff, right? But now think about the rotation axis is completely off of the area again, off of the region. So there's the region, right? And then either the vertical axis or the horizontal axis. When you're rotating that, so if you're rotating this region around the horizontal axis, for example, right? Then think about it again. We're still going to place the stripe, right, to be perpendicular with the rotation axis right here. Okay? And then that stripe, in the way how it is now, like I said, the rotation axis has to be completely off of that area, right? So think about it. And then when you draw the stripe through the region and hits the rotation axis, then some part of the stripe got to be outside of the region, right? And then some part of the stripe is inside of here. But then when you're rotating that, then of course you are going to, I made my picture of it. I made my rotation axis a little too far, so it didn't leave me enough space to draw it. But how about right here? Okay. And so when I'm rotating that, then I'm going to get a picture kind of like this. And I'm not an artist at this point, okay? But you see, so I'm rotating that, it gets me an inner circle being empty disk, right? Empty space. And then the outer circle right here, where we got some material in here, right? Where we got some area there. And so looking at that right here, if we place our eyes looking right at the rotation axis, which is this axis right here, then what we have here now in the as a cross surface right here, as a cross section, is a washer. You guys following? That's the idea. Okay. So think about the center of rotation is right here. That pencil stroke, that marker pointing out, right? So there's an empty space right here, and the washer is like that. So this area right here is a washer, right? And that's the empty space. Does that make sense? Okay. But so in the end, or maybe in another way of how to draw it. Now this time I can draw the exact same pyramid, the exact same picture. I'm trying to make it as closely as possible to that duplication thing. But see, you also have your choice to rotate this thing right around the vertical axis as well. And so in the way it is, think about it, the stripes once again got to be perpendicular to the rotation axis, right? Some part of the stripe is inside the shaded area, the shaded region, but some other part of the stripe is outside, right? And that's why when we're rotating it, we got an inner circle being the empty space, and the outer circle right here is the area that got some material, right? And then so again we got the washer. So no, but in the end, each one of these we call in the usual term we already familiar with from this method right here. We call that this thing right here the cross section, right? Cross section. Okay. And then the cross section here appears to be instead of a disc. It is a disc, but it's not kind of like a disc with a punch, right? With a punch hole in the middle, right around that center of rotation. You guys follow me on that? And so the disc section right here, yes, we call it informal name, it's a washer. Right? There you go. But then in the end, being a washer or being a disc, formally any of these cross sections gotta have a thickness, right? So now you place a stripe perpendicular to the rotation axis. So the thickness is here. You see how thick or how thin that is, right? The thickness here in this case has to be dx, right? Or thickness. There you go. And then in this case, we have placing my washers sideways over here. Once again, the whole point is the cross section got to be always perpendicular with the rotation axis, right? The cross section came out from the stripe, okay? And then this time, in the way how we are placing our stripe here, then each stripe here got the thickness being, and you guys should be well familiar enough with this. It's a dy. Sound good with that, there? Okay. And then, so thickness, and again, thickness multiplied with area. Okay. So I call that the cross section or the washers. Cross section or the washers area. We take the area, see the shaded part right here of your washer, you multiply that with the thickness, any thickness, right? Because here I'm talking about generally regarding about the orientation of your cross surface, but if you're multiplying the area of the cross section with the thickness, we got the volume of one washer, right? I mean, really, you guys ever shop at Home Depot sometimes for hardware? Especially the generators here. You guys ever stop by Home Depot and you stop by those nuts and bolts area? You see, you grab the washer, it's still got a thickness, right? So in the end, that thickness got a volume. See what I'm saying now? And you keep stacking up, and you're going to have a whole column, right, that has volume with it. You got the idea? Okay. And so cross sections area, right, multiplied with the thickness, that's giving you the volume of one washer right here. But the idea is our picture now. See, when you're looking at the whole picture, it's not just one washer. It's infinitely many washers, right? See what I'm saying now? And the space between here grows big or grows small depending on the shape of our regions that define it. Okay? That's why we're accumulating the idea now. We're accumulating all of the washers from a start, right? All of the washer volumes from the start to an end. Okay? That's how we get the volume. So primarily, it's the exact same fundamental with this method that we've learned together. It's about the cross sections area, right? We multiply with the thickness. We're accumulating that all from the beginning, some starting point to some end point. See what I mean? Right. But now a little more specific now. We got to get a little more specific, so I'm going to move over to this board because I want to leave the picture there. Okay, so think about each of the cross sections. It has to appear in the way it is, being a washer. Each washer here as a cross section, right, has to be two concentric circles, right? We're using that term from geometry right there, two concentric circles. So the center of rotation is right here, and so there has to, in the way it is, there has to always be, there must always be big radius, okay, from the rotation center all the way out to the outer circle, right, and then from smaller radius. You guys agree now? Okay, so we can label that. This is, let's call that the big R, and this is little r. Okay. Good. And so in that way right there, then of course it makes sense now that the area, we're gonna have to really dive into that a little bit more. The area of one disk is okay, so the cross section area, right? Let's calculate what that is. So it's 1 bigger disk, pi r squared. But we need to subtract the inner disk, right? Pi little r squared. Is that fundamental enough for that for everyone, right? And so that's why in the situation where we were at, back on the other board, when we're back in this situation, if we're placing our cross sections, right, to be perpendicular. I mean, if our cross sections are perpendicular with the rotation axis, in the x-axis, here, of course, the thickness is dx, right? That's why here we gotta express our radius, the two radii here, the inner radius and the outer radius, each as a function of. These are gotta be a function of x, right? Function of x and some other function of x inside of it. Okay? And so, but then we'll drive into that a little later because my board here is getting a little too busy. Big R, you can see that as some function f of x, and little r is some function g of x. They got to be expressed as function of x, simply because the thickness here, the differential d here already decided to be in terms of x, right? And then in that way, similarly, see right here, right, the big R, right? Big R here, you can call it some function g, or some function, give me some other letter, k, right? K of y. And then the little r has to be some other function. How about h of y? You guys follow it? Got to be functions of y. Right? So now we have all of that, all of those elements here, and ready to put together and drive into a couple examples, right? Right, so right here from that information, it's enough for us to take that into an example here, right? Even though it's similar, but let's call it a new topic here, so I'm going to call it example 1. So I'm going to first point out the rotation axis about the x-axis, right? So we're rotating about the x-axis. The region. Right. Go ahead, spend some time copying it down. We're going to work on that together. All right. And so when it comes to these problems, just like how we were going through the disk method, right? It's very unavoidable that we got to draw the picture. We got to draw the picture for the region that we're about to rotate again, right? And so the description of the problem right now already told us that we're going to rotate the region around about the x-axis, right? So we got to specify the rotation center, and then these are the curves that bound our region here. So our region is bounded by these 4 curves here. So let's go ahead and have a quick drawing of that. So I have to fit it into my small space right here, but and then there's a line y equals 2, which is this line right here. Right? So in between 2 and 4. So let's say 2 and 4. That's the area. Right? So this curve right here. And so it happens to be, for now, that the line y equals 2 right here. This horizontal line and the curve itself, the crosses also at x equals 2. And you guys can easily verify that, right? I mean, scratch work can quickly tell you that, hey, we're setting 1/4 x squared plus 1, right, to equals y equals 2. Equals 2 like that, right? Subtracting the 2, I mean the 1 from both sides, and multiply both sides by 4, we're going to have 4 coordinates. Not rough step here. 1/4 x squared equals 1, right? And then you can multiply both sides by 4, you're making it x squared equals 4. Right? That means we've got 2 crossing points here. X equals plus minus 2. That's why minus 2 is here, right? And positive 2 is there. And that's easy. I'm pointing out that it should be easy to verify that, right? That we have to have that crossing point. And so between x equals 2 and x equals 4, that's the region right here. Plus, it's that region where the 2 curves are crossing, right? And then the other one is the point, the x value where we just set it out. So we got that picture right there. So now, after we've had that picture, right, then once again, the rotation axis is the x-axis. We're rotating that around the x-axis. And we're placing our eyes to look straight at that. So now each stripe, we draw the stripe right here. When you're rotating that, the stripe got to be placed, right? The stripe got to be placed perpendicular to the rotation axis. So it's looking at that way. Now we're going to have an inner area, right? And there's an outer area. You guys know that still? Okay. And so that's how we're getting a washer over here. So the red picture over here is washer, the inner circle, right? The inner 3D circle right there is going to be my empty space in that, right? It creates the whole thing, the whole picture there is a washer. Good. So now we're gonna just have to lay down the work here, all the elements that we need. So the thickness for a washer like this, right? Since the washer is being placed as a cross section, the washer here is being placed perpendicular with the x-axis, right? So that thickness here got to be, right? So the thickness for our problem here got to be written as a dx. That's all it. Okay. And then now it comes to the cross section area. Okay. Cross section as a washer, right? Area. So it comes to, right? Let's come up with a generalization right here. Remember, the picture is here. For any washers, we need the pi times the square of the longer radius, right? Minus pi times the square of the little radius, okay? Because it's outer circle minus the inner circle. And so in this case here, the longer the radius going from the rotation center out to the upper curve, right? So it's a 0 down here, and it hits all the way up to the 1/4 x squared plus 1, right? So that's the outer radius. And so the outer radius here I'm looking at, right? Pi times minus 1, it's not minus, it's just 1/4. Pi times 1/4 x squared plus 1. So that's the outer radius, but as area squared, right? So it's pi times 1/4 x squared plus 1 all squared. And then we need to subtract the inner radius. The inner radius stays constantly in 2, 2, 2, and 2. Do we agree on that so far? So it's going to be pi times 2 all squared. Please, anyone have any question for me on this? And then we can check for consistency at this point that since we have decided our thickness being the dx, right? And so all of our radius, all of our radii are expressed in terms of x as functions in terms of x. Right? So now we're ready for putting the pieces together. So cross-section area multiplied with thickness. Here we're looking at pi, right, times, and I can factor out the common factor of pi right here. So pi times, then there's a 1/4 x squared plus 1 all squared minus 4, right? So this is the cross-section area multiplied with thickness. We got the volume of one disc, right? One washer, and then we're accumulating all of the washer's volume from. So this time, where do we start the accumulation? From this starting point, right? And all the way to ending at x equals 4. The picture is making it clear, right? So this way, right here, I'm going from 0, right, to, this way I'm going from 2 to 4. That's how we have had the complete setup for our integral ready for action. So now it's just a matter of, well, we can algebraically FOIL around this, and that's the only option we have for this integral. Right? So you can FOIL around this 1/4 x squared plus 1 like that, and then subtract 4. So my board is getting a little tight here, so pi. I can also bring that coefficient pi out front. So the integral from 2 to 4, okay. And then this after FOILing out, we're looking at the 1/16, right? That's x squared. Plus 1/2. Oops, this is actually the 4th actually. Plus 1/2 x squared plus 1. We have minus 4, so it's going to be altogether a minus 3. Okay. Dx. That's how I'm formulating my integral right there. It may be a little bit blocking for some of your view here. You'll be hidden behind those podium computers. So 1/16 x to the 4th plus 1/2 x squared minus 3. My 4th power is a little hard to read. Just adjust that. Right. Okay. So now it's just a matter of taking your time to find the integral for that, right? To go find the antiderivative for that. So it's just now one more step, and then for the real final calculation, I'm going to leave that for you to complete. Right? So it's pi times, and here we have a 1 over, so 16 times 5, right? And it's going to make it 80 right here, right? 80x to the 5th, plus a 1/6 x cubed, and minus 3x. You guys follow it? And we're evaluating from 2 to 4. So this time you've got to pull out your calculator and do some good calculation for me, because I need some good result for you. It's not simply just a 0 in the lower end right there anymore. So let's do some good calculation. Be careful with your calculation as well. And keep things in fraction if you can. So for now, leave the pi completely out, right? And after this calculation right here, substituting in, you can just end up with a final fraction for it, making it easier to keep track of. Does your calculator have that flexibility to convert between decimal and fraction? Okay, so I found the answer up here, and you can compare with me. Okay. But in fractions, when we're looking at the 236 pi right here, I kept it all in exact expression over 15. 236 pi over 15. Okay. That's the work of that. All right, so we're still in example 1, but let's call it part B of the example. Sounds good? So there's nothing much about to change here. Pretty much the whole problem remains the same. The 4 curves that generate our region also remain the same. I'm only going to rotate about the y-axis, okay? So let's call this part B. That's why you didn't need to write down too much. Find the volume of the solid, right, generated by rotating about the y-axis, right? All right, that's the only change, and we call it part B. You're gonna be surprised with how much we can do with one given region, and when the center of rotation is kind of like off from that, right? We have just because we put a different rotation right there, we're gonna end up with a different picture, a different solid, a different volume as well. Right? So those are still the 4 curves again. So if you need to, you can spend some time writing it down, and then we're gonna get onto that. Same exact region, right? We bound by the same exact 4 curve. It's just we change the rotation axis. That's all. So the picture is like this. Okay. So there's your parabola, right? And there's maybe it's a little too. There you go. We know it's 2 here. It's bounded by x equals 4. The rotation axis this time goes this way. So this is the area. Right? But now, as required, we're rotating that. We're going to rotate that area, that shaded region here around about the y-axis, right? So you got to think about putting your stripes, right, sideways, just like that. Is what I'm saying up. Your stripe is going sideways, right? Perfect. So the rule of thumb is the stripe is always perpendicular to the rotation axis. And then there's some part of the stripe being the outside of the region, right? That's why I'm putting up those in dots there. Good. And so rotating that, right? And we're gonna create we're gonna have the inner space right here is being empty, right? And then the outer space right here has some material. That's why we got a washer. Good. The washer in this case here is like the thickness, right? This is how I see the thickness. That's how I see the thickness. So the thickness here in this case, do you guys want to give me a decision? What should be the thickness that we're expressing here?
Yes.
What's that?
Dx.
Dx.
Right. Y.
It should be dy, right? It's sideways there, right? Yep. There you go. Dy. Right. Now let's look at the cross-section area. Cross-section. But now when I'm cutting short my wording with cross-section, I mean the area of the cross-section. Right? We need outer circle, subtract the inner circle to get the washer's area. So the only challenge now is that we got to convert these, right, into, you see, each one of the stripes here, the outer area is going to be that distance from the rotation center out to the further right end of our region, right? And then from here, the inner radius has to be anywhere from the rotation center to where it hits the left end, right, of our rotation, of our rotated area. So we got to convert those into curves in terms of y function, right? The y function. So now let's do a little bit of a scratch work right here. Okay, so that line right here, it's x equals 4, right? X equals 4, that means as a function, it's already a function. X equals 4, constant, right? But then the other curve right here, we got to do a little bit of work. See, it was written originally in a problem right here, 1/4 times x squared plus 1. this left side of the region is here, the left side is there, right? And so that belongs to the curve. So we need to rewrite this curve right here as a function in terms of y. Right? So now I'm going to subtract 1 from both sides. So y minus 1 equals 1/4 x squared. That's simple. And then I'm going to multiply both sides by 4 to get rid of that 1/4 right here. That makes it 4y minus 4, right, equals x squared. That's simple. And then we're going to take the square root, right? So take the square root both sides, but remember, be cautious that anytime we're taking the square root both sides, we're going to have to go with a plus and minus. So plus and minus 4y minus 4 on the opposite side again. Right? And then we have to make a choice. Which one are we choosing here to be the appropriate one? It's this side right here. It's this side, meaning it belongs to the positive x value, right? On the right-hand side, the positive x value, that's why we've got to choose the positive square root. Sounds good? All right. And so, now we just know that the larger radius, big R, right, has to be the positive. Big R is actually only 4, but the little r, right, is positive square root of 4y minus 4. Right? Just note it down, it doesn't hurt, right? A little bit of space for the extra step like that. All right, so now we're going to multiply that together. So area of a cross section, here's how we go. Pi times 4 all squared, right? Area of the outer circle. We're subtracting pi times square root of 4y minus 4 all squared. Right? Area of the larger circle, subtract the area of the smaller circle. Right there. That cross-section area we multiply with the thickness, dy. Okay. Let's now check for consistency right here. Our thickness expressed as a differential dy, right? Is it consistent with all the variables we involved here? Yes, it's all in terms of y. Okay? So now that way right here, I am going to be accumulating, because the whole one thing right here is the volume of one thin washer, right? We're going to be accumulating all the washers from, so start to end. So start to end in this case, because we're putting the stripes horizontal this time, right? It needs to be perpendicular with the rotation axis. So that means we're stacking our washers from bottom up, right? Bottom up, okay. Right? So do you see that in the picture? Bottom is this low end right here, right? And up point is there. So we need to do a little bit of solving work again to find where's the up point, because the low point is down here, which was already given. This line, right, is y minus 2. So we know that the low is 2. Are we good? We know that the low is going to be 2. But where does it hit the high again? So the high is where this line x equals 4 hits into the curve, right? You guys agree on that? Okay? So the curve itself, we can say with the original version of the curve. The original version was a y equals 1/4 x squared plus 1, right? So when x equals 4, you go y equals 1/4 times 4 all squared plus 1. Because when x equals 4, we want to find out what y value it reaches, right? So 4 squared is 16, cancel with 4 here, giving it a 4. The whole thing here turns out 5, right? So our accumulation stacking up from 2 to 5 there, right? We're stacking up the washers, right? From the low, the bottom one being 2, right? The high one being 5. That's how we have completed our integral right here. And that will get us our volume V. So now we're gonna just go ahead and advance, right? And then we got quite a few advantages right here, because the square root cancel with the square, right? And then we can pull out the pi right here in front. And so in the next step, I can use a little space right here, integral, or how about let's put the pi in front, right, as a coefficient. So coefficient pi times the integral from 2 to 5, right? And then we're looking at now 4 squared is 16, right? I'm subtracting y. I'm subtracting 4y minus 4. No more square root, right? And you see, I can fit it all into that narrow space of my board. Okay. Agree with my next step, okay? And so in that way, here we're looking at, and one more step. Let's just clean up the terms before we proceed. Okay. 16 minus negative 4, making it a plus 20, right? So it's a pi times an integral from 2 to 5, right? And then we're looking at the really 20 minus 4y, right? dy. This is the last setup right here. Now we're ready to really integrating it, right? So we're looking at pi, right, times now it's a 20y, right, and minus a 2y squared. I'm assuming that you have already been through it with how you find antiderivatives. I hope I'm not too rushing for anyone's work. Are we okay? Right. So now you can go ahead and take your time calculating that, right? All right, anyone?
I got 18 pi.
Got 18 pi. I agree. Thank you. 18 pi. Right, so at this point here, as far as the work for getting this done, right, you've seen enough detail here. So let me bring in one more example here for that. Okay, let's call it example 2. Okay, so when it comes to that, right? So now let's look at the picture. We gotta draw the picture. It's unavoidable. X equals 2y, right? Maybe we're not too familiar with things like that, but you can quickly see that as a y equals 1/2 x by dividing both sides by 2. Right? So that makes it, but that gives us a line being a half slope, right? So you go into 2 over, right, and then 1 up, okay? So there's your line. Okay? Good. That's our line there. But then what about the other curve? Y squared equals x is a sideways parabola, right? It's a parabola but going completely sideways like this. You know what I mean? Right? So the scale 1 is about here, so I'll have that. Scale 1 is down here. There's a sideways. Right? Now the question for you is, where is that region? Because the term here, I purposely brought it in a problem like this, so for you to recognize it. When it says that enclosed by, right, that means you are only given 2 curves here. There are some areas where the 2 curves are crossing each other, right? Some point where 2 curves are crossing each other, and then crossing again here. So inside completely, that's the region that we call the enclosed region. Right? Because the area out here, that's not enclosed, right? The area down here, that's not enclosed. The area here is not enclosed. Only there is the part that's completely trapped inside. Right? So sometimes the description can go a little short like that, but we've got to understand the way how the language runs, right? And then be able to identify. Okay? And so now with this enclosure here, all right, so now we're ready for action. Rotating around the x-axis, meaning our rotation axis is here. Okay? So the stripe, each of the stripes got to look like this. We're going to draw the stripe being perpendicular to the rotation axis, right? And so the part that being dotted over here, because it's outside of the region. You guys with me on that bit there? Okay? And so now when you're rotating it, you're going to end up with, you see, inner, actually I'm drawing it a little bit incorrect for here. Okay? And then there's the outer that hits like that. Sounds good? That's our washer right there. All right, so now you're experiencing enough of the 2 earlier problems, right? So let's look at the thickness right here. How do we express the thickness? Should be what? The x here, right? And then the cross section as a washer. Okay? Cross section as a washer. Okay? Or washer is an area. What we need here, outer radius minus, the pi r, big R square minus pi, the little r square. So in that way, we need to convert, so think about the big pi, the big R here, from the rotation center out to that. We need to express that as a function of x, right? The larger radius here needs to be a function of x. But the function of x here comes from this curve here. We got to express that curve being a function of x. Are you following with me on that? Yeah. But the curve itself here is sadly given in terms of y, right? So we have to do a little bit of algebra here. So scratch work right now. Right? Y squared equals x. Are we good? That means y equals plus minus square root of x. We have that still. And then we're looking at the picture, the side of the picture where the y value is on the upside, right? It's on the positive side. That's why here it makes sense that we only pick y equals positive square root of x. That's how we write our curve, right? So the outer area, so the big area, the big radius is square root of x. Okay. And the smaller radius, the shorter radius, is from the rotation center out to wherever it hits that line like that, right? You guys with me on that still? It hits that line like that. So again, x equals 2y. That was given in the equation. We want to solve for y here. So I'm dividing both sides by 2. Right? That gives me a 1/2 x equals y. Okay. And so the little radius here is 1/2 x, expressed as a function of x. Okay. So now we're ready for putting the cross-section area together. Pi times the square root of x squared, so pi big R squared, minus pi times little r, right? 1/2 x all squared. Okay. So now in that way, let's go ahead and accumulate. Let's go ahead and set up the integral. So once we've had those elements together, pi times 1/2, square root of x squared minus pi times 1/2 x all squared. Right? Multiply with the thickness, we get the volume for one washer, and then we're accumulating. Okay. So where's accumulating happening? Well, it's easy to recognize here, right? But then what about that other point of that? See what I mean? What about that other point? So it's best that we solve these values here. You can directly solve right here. Hey, let's set these, see, it's x equals and x equals, so let's set directly y squared equals 2y. Let's do it that way, okay? And then we come up with some y value. We can also calculate the x correspondingly, right? So we solve this equation for y, making it to y squared minus 2y equals 0, right? Factor out the y right here, looking at y minus 2 equals 0. We good with that then? And so that means our equation comes out with two values, y equals 0 and y equals 2. So y equals 2, it's up here. Y equals 2. And y equals 0. Y equals 2, y equals 0 is down here. But y equals 2 has to correspond to what? X value. Y equals 2 corresponds to, and you can use either one of the equations here to come out with the x value, right? So x equals 2 times 2. So that leads to x equals 0 and 1, and also x equals 4, because you can use, at the crossing point, you can use either one of the two equations right here to calculate your x value, right? You guys okay with my explanation right there? So now the accumulation happens from 0 to 4, right, on the x-axis. That's how we set up our volume calculation as an integral. Right? Now the next step here is just, yes, I'm going to take the pi out front, right, as a common factor. Integral happening from 0 to 4. Square root is going to get canceled with the square, so I have x, right, minus, so the 1/2 x all squared here is 1/4 x squared. So the integral now turns out surprisingly simple, right? So it will become, here antiderivative gives me pi, and then we got 1/2 x squared minus 1/12 x cubed, right? We are integrating from 0 to 4. Okay. So in my calculation, it came out 8 pi 3. Always double check my calculation.